Alright, welcome. Today we're going to talk about inelastic collisions. Last time we talked about bounce collisions, now we're going to talk about inelastic collisions, still using conservation of momentum. First off, we have to talk about this idea of elastic versus inelastic. And what we've done so far is we've had collisions where the objects bounce off of each other, right? So if we have an object, and they're moving towards each other, well, then afterwards, they hit, they bounce off each other, right? Typically, but not always, they go in opposite directions. What happens in an inelastic collision, right? What do these words mean? For an elastic collision, kinetic energy is conserved. This is for an elastic collision. An elastic collision is any collision where kinetic energy is conserved. Inelastic, you can probably guess, if elastic is where kinetic energy is conserved, inelastic collisions are where kinetic energy is not conserved. In an inelastic collision, kinetic energy is not conserved. You might see this little small note we have at the top. For a completely/perfectly inelastic collision, the objects stick together. Okay. A perfectly inelastic collision. It's just an inelastic collision, right? Kinetic energy is not conserved, but the objects stick together. So a perfectly inelastic collision is an inelastic collision, so kinetic energy is not conserved, and the objects stick together. Earlier, we did bounce collisions. Objects hit each other, they do not stick together. In an inelastic collision, the objects hit and stick. Perfectly inelastic, what does that look like? It might look like, well, if you have one object right here, it's moving to the right, another object that is just stationary, it's not moving. Afterwards, they hit, they stick together, both objects are now moving to the right. For kinetic energy, just a little refresher, what is kinetic energy? We have a formula for it. It's the energy of motion, 1/2 mv squared. It is measured in units of joules. It's very similar to momentum in a lot of ways, right? Momentum is mass times velocity. Kinetic energy is in joules. Momentum is in kilograms meters per second. What we need to be careful with is just making sure we remember the differences, right? When we're solving for, say, kinetic energy, or when we're trying to verify if something is elastic or inelastic, the only difference is kinetic energy being conserved or not. Just make sure you're using the proper equation for kinetic energy to determine if it is elastic or inelastic. All right, let's continue on with our example. Now, what does this actually look like? For our inelastic collisions, we're really going to make them perfectly inelastic, where the objects hit and stick. It's not that every inelastic collision is a perfectly inelastic collision. It's just a different type of collision problem that gets a bit trickier that we really want you to be comfortable solving. With conservation of momentum, earlier we did bounce collisions, right, where the objects hit, they bounce off. We should be comfortable solving those. Now this is a new type of problem. What if the objects don't bounce off, but they hit and they stick together? Let's investigate. Let's try this out. The setup is going to be much the same. We have a before picture and we have an after picture. I'm going to draw the objects. I just draw them as squares. Keeps it nice and simple. 20 kilogram medicine ball. Here's our medicine ball. 20 kilograms. It's thrown with a velocity of 5. Since it's given as positive, I'm just going to say, all right, it's thrown to the right, positive direction. To a motionless, here is the child on a skateboard. The velocity is 0. We do not know their mass. At least not yet. Then, draw the after picture. The child and skateboard have a combined mass of 60 kilograms. Calculate the velocity of the child's skateboard ball after the child catches the ball. Okay. Here, reading this again, this is our medicine ball. This is the child on the skateboard. In this case, it might be just a bit easier to keep track of everything since we have so many objects to actually draw out the objects, right? Here's the medicine ball. That mass is 20 kilograms. Then we have the skateboard. Here's the wheels and the child. What's the mass there? They have a combined mass of 60 kilograms. In our after picture, right, we say the child catches the ball. We want to calculate the velocity of all of them, the child, skateboard, and ball, after the child catches the ball. Well, what does this mean? Afterwards, we don't have two separate objects anymore, right? Now, the child has caught the ball. Here's the ball. Here's the child. They're holding on to the ball. They've caught it. They're still on their skateboard. Now, well, we can assume, we know, if the ball is moving to the right, the child catches it, they're going to end up moving to the right after they catch it. The question is, just how fast are they going to the right? Now, what we can do here, the way we set this up before, and the reason we did bounce collisions before, is it's the same exact setup. We say, use conservation of momentum. The total momentum in our system, which is all of our objects in this case, is going to equal the total momentum of our system after the collision. Before and after, the total momentum is equal. You can split this up. The momentum of object 1 plus the momentum of object 2 is your total momentum before and after, right? These are P1 prime, P2 prime, momentum of object 1 before or after, momentum of object 2 after. We set it up just like we did with bounce collisions. Replace these with our variables, m1v1 plus m2v2 equals m1v1 prime plus m2v2 prime. Now the trick is, you could plug in and you get to a point where you don't have enough information. You start plugging in, you say, okay, 20 times 5, we can do that. 60 times 0, we can do that, no worries. But on our right-hand side, we have the mass of object 1. That's our medicine ball. We don't know how fast it's moving. We have the mass of the child and skateboard. That's 60. We don't know how fast they're moving either. You have two unknowns in this equation, and it seems impossible. But there's a special trick. When you have a perfectly inelastic collision, your setup is the same, right? We still ended up with this big equation, m1v1 plus m2v2 equals m1v1 prime plus m2v2 prime. Just total momentum before equals total momentum after. The special case is when the objects stick together. They hit and they stick and they travel as one together. What you're going to do is you can treat the objects, instead of separate objects, treat them as one object with the same velocity. If the child is holding on to the ball and they're on top of the skateboard, they are all moving together as one object. When they hit and stick, they're going to move like this. They move as one object. They're not going to move separately at different velocities. They're moving together at the same velocity. So we don't really have two separate velocities here. The velocity of the ball and the velocity of the person and skateboard after they catch it, they're going to be the same. Instead of writing these as different velocities, we can group it. We can say these are really both just our velocity v. since v1 prime equals v2 prime, we can just call them some velocity. Maybe you'd like to call it velocity final. You can go ahead and do that if you like. So this is in the math and how we plug it in. Let's bring this down so we can talk a little bit more about rearranging our equation. The way we get here. With a collision, you can always set up your big conservation of momentum equation, but what is different depending on the type of collision you have? If you know the objects hit and they travel together after the collision, these are no longer different velocities. These are the same. You end up with, okay, on your right-hand side, this is m1 v final plus m2 v final. Your left-hand side, pardon me, is still the same, right? Nothing over here is changing. It's still two separate objects, and they're colliding. But afterwards, they end up with the same velocity. This means you can pull out a velocity and just combine the objects. This is m1 plus m2. Treat them as one object. They're traveling at the same velocity. Left-hand side still stays the same. Miss this 2 right here. So then you can see, when we're plugging it in, it can be even more convenient to just go ahead and combine those masses, right? Mass 1, that's the medicine ball, 20 kilograms. Mass 2, that's the child and skateboard, 60 kilograms. They're traveling at some velocity together. It's not a different velocity. They're attached. They're traveling together. Now we just solve it like we did before. 20 times 5, this is 120. Wait, nope, that's 100. Mental math. 60 times 0, this is of course 0. So our total momentum is 100. That's not going to change. Our total momentum afterwards must also be 100. 20 plus 60 gives us 80 times our final velocity. Go ahead, do a little bit of division. If we plug in 100 divided by 80, we will get 1.25 for our final velocity. Again, pay close attention to your signs here. This is a positive, so that means they are moving in the positive direction. Overall, what changes when you have an inelastic collision, especially a perfectly inelastic collision? You still set it up the same way. You do not need to show me all of this. Every time you have a collision, you can just jump right to this equation, right? Conservation of momentum, the big equation in green. At that point, you just have to decide, is this a collision where the objects are separate after the collision? Like, is it, say, a pool game where you hit one ball into the other and they bounce off of each other? Those are separate objects. You would just keep this green equation like it is, plug everything in to solve. But if they hit and they stick together, and to decide this, you'll have to read the problem carefully, right? Is someone catching a ball? Is someone wearing a backpack and running with that backpack, right? Are the objects coming together and moving together? If they are, treat them as one object. You end up with this equation in purple. Combine their masses after they collide into just one big mass traveling at some velocity. And at that point, you can plug in to solve. One last thing before we finish. Say we're asked an extension here, and in this example we're not. Say we are asked, is it a perfectly, we know it's a perfectly inelastic collision, but let's prove, is it inelastic, right? Is kinetic energy not conserved? Well, you'd have to do a whole nother calculation. And we'll go through, it's very, very, very similar. We're just going to take all of this. Since we just went through these notes, I'm going to go ahead and get rid of this. How do you set it up to see if it's inelastic or not? Well, you'd have to do all that work kind of again, but in a bit of a different way. You still have a before and after, but instead of comparing momentum before and after, you know no matter the type of collision, momentum is always conserved. But is the kinetic energy conserved? Well, figure out your kinetic energy before. Figure out your kinetic energy after. Again, this is your total kinetic energy. We don't know if they're equal or not. This is what we're investigating to see. The total kinetic energy is the kinetic energy of each object. Do it just like we did momentum. The kinetic energy of the first object, 1/2 m1v1 squared plus 1/2 m2v2 squared equals, well, not necessarily equals, we don't know if it is, 1/2 m1v1 prime squared. We really only have our one object. So this, remember, we're combining the masses. This is 1/2 m1 plus m2, since they're traveling as one object, traveling at our final velocity, squared. Okay. Don't forget to square this as well. Now we plug in. Okay, we know this is just going to be 0, right? The child and skateboard, they're not moving. They have no kinetic energy. But the medicine ball, it is moving, and that's going to have kinetic energy. The mass is 20. The velocity is 5. If we square 5, we get 25. 25 times 20, let's do that. That gives us 500. Cut it in half. We get 250 for our total kinetic energy before the collision. Let's compare that. What do we get after the collision? Well, 1/2. The mass, 20 plus 60, this is 80. And the final velocity, we just solved for it. I deleted it, but it was 1.25. You can now square that velocity. 1.25 times 1.25 times 80 times 0.5. 62.5. These energies are nowhere near the same. We can see in total, our system, momentum is always the same for any type of collision. Doesn't matter if it's elastic, inelastic, perfectly inelastic, momentum is always conserved for a collision. What we don't know is kinetic energy. If it is conserved, great, we call that an elastic collision. If it's not, we call that an inelastic collision. So here, we can see plainly the energy, the kinetic energy, is not conserved. This is an inelastic collision. Specifically, since they hit and stick together, it is a perfectly inelastic collision.